All right, so what we're going to look at in the lesson today is some rules for definite integrals, and when we're using definite integrals, what we're talking about is finding the area under the curve, finding those ways that we can find those regressions of area under curve, finding those ways that we can look at the distance something has traveled, and that's how integrals work. And so we've got some rules for those definite integrals. Now, I just want to just point out one thing real quick. These rules may not all make sense right now. And I want to emphasize they may not all make sense right now. But as you start going through and using integrals in your daily calculus practice, these rules start to make sense. It's kind of like talking about limits. We have all these rules for limits. They're really difficult to understand at first when you just look at them in generalities. But then when you start to work through limits and do limits and practice limits, some of those rules start to make sense. So here's all these different rules. We're going to look at them right now. And some of them we're going to use a lot, and some of them just not very much at all. But these are the rules, okay? And I would say that of these, some of these most important ones would be 1, 2, 3, and 4. These are going to be the ones that you use the most, period, end of story, in almost every definite integral problem you do. You're going to use 1 through 4. 5, 6, and 7 are a little bit different. They set up a little bit different. They work out a little bit different. And you'll know these situations when they show up, okay? And so anyway, these are all the different rules we're going to look at with a primary emphasis on 1 through 4, all right? So take a second. Make sure you have these rules written down on a some sort of trig sheet or study sheet or calc sheet or whatever that you're going to use so that you can refer back to them while you're working. And then we'll look at the next slide and we'll put some of these different rules into play. All right, so here are some examples that we can try out that use some of these different rules for finding integrals, okay? And we're not told exactly what the functions are. We're just going to try and use these rules to sort out what goes where and how. So one of the rules said that if I take my 1 to 4 and I switch it around, then that would be the same thing as negative 1 to 4. So I've got that guy. I've got that rule right here. It's negative 2. So it's the same thing as negative 2. All right? So that's one of my rules right there. Hold on, let me find my rule sheet also. Okay. What about from negative 1 to 4? Well, that's the same thing as going negative 1 to 1 of fx dx plus 1 to 4 fx dx. And so if I look at one of my rules, I can add the integral things together, the different integrals. So what do I have? Well, negative 1 to 1 is 5. And 1 to 4 is negative 2. So 5 plus negative 2, or 3. What about this guy? Oh boy, what's going on here? We've got negative 1 to 1 of 2fx plus 3hx. So let's separate this out. We'll use our rules again. We're going to go from negative 1 to 1 of 2fx dx plus negative 1 to 1 of 3h dx. 3hx dx. Let me make that better here. 3hx dx. Okay. Well, one of my rules said, I could add or subtract these integrals together, so I switched to adding. The other rule said I can move the constant out in front, so I have 2 times negative 1 to 1 of fx dx plus, and then I can move the 3 out and go from negative 1 to 1 of hx dx. And so what do I end up with? I end up with 2 times this guy, 5, 2 times 5, plus 3 times this guy right here, 3 times 7. And so that's going to be 10 plus 21, or 30. Let me double check that. I think that's where we went. Hold on one second here. Let me look at my book. Yes. All right. Righto. Okay. Now, look at D, 0 to 1 fx dx. I don't think we're going to have enough information to solve this out. There's no way that we could subtract one of these around to get to 0, just 0 to 1. And so on this particular one, D, we just don't have enough info, not enough info. Now, if we had another problem, or if we had another rule that we could use, or if we had a kind of a little bit of a different situation, we'd be okay. All right. What about the next one? The next one goes from -2 to 2. Well, kind of the same thing. Kind of the same thing as on D. There's really not enough info. I can go from -1 to 1, but we don't have a rule for multiplying our limits of integration by a constant. Like, we don't have a rule for that. So there's really not enough info for that guy. Now that takes us to F. Well, I can rewrite F as -1 to 4 of f of x dx plus -1 to 4 of hx dx. I can do this guy. This is -2, but I can't do this guy because, again, I don't have a rule for him. I don't have a rule to go from -1 to 4. I've only got one h of x guy, and he goes from -1 to 1. So this guy also would be not enough info. Like, I need a little bit different info. Maybe another integral to look at to figure out exactly what's going to work best to add those together. But there's how you use some of your basic rules. A, B, and C, you're going to do a lot in your calculus courses. D, E, and F, you won't see so much in the future, but it's good to recognize, when you can and cannot use rules. All right, here's an average value problem, okay? If F is an integrable function on A to B, its average value on A to B is 1 over B minus A, that gets us our average part, times the integral from A to B of f of x dx. And that'll give us some function at C. Some point C, we'll find the value for that, okay? So use this pattern to find the mean value of f of x equals 4 minus x squared on the interval from 0 to 3. Does f take on this value at some point on that interval? So what are we talking about? Well, we're talking about if A is equal to 0, B is equal to 3, we're talking about the integral of, we're talking about 1 over 3 minus 0 times the integral from 0 to 3 of 4 minus x squared dx. Okay? And so in order to work this out, there's a couple different ways that you can do it. I give you permission right now, I give you my blessing to plug in this guy into your calculator to get an answer. Okay? Plug that guy into your calculator to get an answer. We'll talk specifics later, exactly how to do this and all that. Okay? And when you plug that into your calculator, you're going to get 3. So I end up with 1 over 3 times 3. And that's going to be 1. So the question is, if we look at 4 minus x squared, so it's going to be something like a graph like this, okay, from 0 to 3, all right? Is there some place that our value, our f 4 minus x squared equals 1, okay, because that's our average mean right here. This is our average value right here. This is our mean value. So let's do that. We'll take 4 minus x squared equals 1. We want to know, where is this true? Subtract 4 from both sides, and then divide by your -1 so that x squared equals 3. What we're going to discover is that when x is equal to the plus or minus the square root of 3, it's equal, the function is equal to its mean value. All right? However, the interval that we're looking for goes from 0 to 3. So there's only one spot where this happens. When x is equal to radical 3, it's equal to its average value. In other words, 4 minus radical 3 squared is equal to 1, which is its average. And that's what we're trying to show. Okay, on this problem, what we want to do is we want to evaluate an integral by using the antiderivatives, the antiderivatives. And this is the nuts and bolts of definite integrals and using what we've learned about derivatives to solve them out. So try using this formula right here. The integral from a to x of f of t dt is equal to f of x minus f of a. In other words, that antiderivative function evaluated at x minus the antiderivative function evaluated at a. So let's just ask ourselves real quick, what is the derivative? The derivative of what? Is equal to the sine of x. And this guy right here, this derivative is what we're really interested in, okay? And so we're going to figure out, no matter how you do it, just think about the derivative of what? And so you should arrive at the negative cosine of x. And so then what we want to do is we're going to use some like fancy stuff here. We're going to say we're going to evaluate this from 0 to pi. Well, what does that mean? That means we're going to follow this step right here. F of x for this problem, f of x is negative cosine x. So what are we going to do? We're going to stick in our upper limit, pi, and we're going to stick in our lower limit, 0. So what we're going to end up with is negative cosine of the upper limit, pi, minus negative cosine, the lower limit, of 0. So the cosine of pi is negative 1, so minus negative 1, minus, and then the cosine of 0 is 1, so minus 1. And I end up here with 1 plus 1, or 2. And that is how you evaluate a definite integral using antiderivatives. The derivative of what gives us this thing in here? That's the question that we're asking. And then we're going to use our upper limit and our lower limit to complete that process. It looks kind of weird and strange, but once you've done it a few times, what you're going to realize is you're taking the stop part of our derivative, the stop part of our function, not derivative, the stopped part minus the start part. And you know what? You've been doing that all year long.